Good evening, everyone. So, in this lecture number 4, we'll be discussing some of the problems related to motion along a straight line but under constant acceleration, right? In the last class, we discussed about the different equations of motion under constant acceleration. And these were the four equations that we derived in the last class. And in this lecture also, we'll be deriving the fifth equation also. That's the distance traveled by the particle in the nth second. And before doing so, we'll be discussing some of the questions related to all these equations, right? So let's start with the question number one. The question number one is on the screen. It's a train traveling at 20 km per hour is approaching a platform. A bird is sitting on a pole on the platform. When the train is at a distance of 2 km from pole, brakes are applied which produce a uniform deceleration in it. At that instant, the bird flies towards the train at 60 km per hour and after touching the nearest point on the train, flies back to the pole and then flies towards the train and continues repeating itself. Calculate how much distance the bird covers before the train stops. So the train is at a distance of 2 km from a pole, right? And the train is approaching the pole at a speed of 20 km per hour. So let's suppose that this is a pole here, and this pole is at a distance of 2 kilometers, right? This pole is at a distance of 2 kilometers, and the train is approaching this pole at the speed of 20 kilometers per hour, right? At a distance with a speed of 20 kilometers per hour. Now, what happens is that the train stops after some time, right? We will try to calculate after how much time the train actually stops, right? So when the train stops, its final velocity will be equal to zero, right? Its final velocity will be equal to zero. So we can use this equation of motion, that's v square is equal to u square plus 2as. And as here is the displacement, and the displacement when the train stops, right? When the train stops, it stops just before when the train is at a distance of 2 km from pole, brakes are applied, which produce a uniform. At that instant, the bird flies towards and touches the nearest point of the train, flies back to the pole, and then flies towards the train and continues repeating. Calculate how much distance the bird covers before the train stops. So when the train stops, final velocity will be equal to zero, right? So v will be equal to zero when the train stops. So from here, our deceleration will be nothing. It will be equal to a, that is equal to minus u square upon 2s, right? Minus u square upon 2s. And let's suppose after covering this 2 km distance, the train stops. So it will be 20 square upon 2 into 2 will be the displacement. So it will be 400 over 4, the negative sign, right? So it will be minus 100. So minus 100 will be the deceleration of, that is minus 100 kilometer square per hour, right? So this will be the deceleration in this train, right? Now, during this deceleration, we have to also calculate how much time this train takes to stop, right? How much time this train takes to stop. So once again, we can use this first equation, that is v is equal to u plus at, and for final velocity to be equal to zero, so the time will be nothing. It will be u upon a, right? It will be u upon a, or we can say that the time taken by this train to stop is 20 over 100, right? So it's nothing. It's 1 upon 5 hours, right? So, or we can say it is 0.2 hours. So 0.2 is the time taken by this train. 0.2 hours is the time taken by this train to stop, or we can say 12 minutes, right? 0.2 hours is equal to 12 minutes. So 12 minutes is the time taken by this train to stop. And during this time, what happens is that the bird flies, the bird touch the nearest point on the train and flies back to the pole and then flies once again towards the train and continues repeating itself, right? So for this time, when the train stops, means the bird continues to fly for these 12 minutes back and forth, from the pole to the train and from the train to the pole, right? So we have to calculate the distance covered by this bird, right? And the speed of this bird is 60 kilometers per hour. The distance that bird will be traveling, the speed of this bird is given as, so it will be distance. Let's suppose distance is x and the time is t, and we know that this bird must be moving for 0.2 hours, right? And velocity of this bird is 60 kilometers per hour. So v is equal to 60 kilometer per hour. So a distance traveled by this bird will be 60 multiplied by 0.2. It will be equal to 12 kilometers, right? So the bird will be traveling 12 kilometers during this time when the train stops. Let's move on to the next question number 2. And the question number 2 is, two trains traveling on the same track are approaching each other with equal speeds, right? So suppose that we have two trains. One train is here, train A, and we have train B here, right? These are the two trains which are approaching each other with equal speeds. The speed is 40 meter per second each. They are approaching towards each other, right? And the drivers of the trains begin to decelerate simultaneously when they are just 2 kilometers apart, right? They are just 2 kilometers apart, means when they start decelerating, they were approaching at a speed of 40 meter per second each. So they were 2 kilometers apart, or we can say they were 2000 meters apart, right? Assuming the deceleration to be uniform and equal, the value of the deceleration to barely avoid collision should be. So we have to calculate the value of this deceleration so that the two trains just avoid the collision, right? So it means that these two trains will be approaching each other. They will just stop before colliding each other, right? Like this. So this will be the situation, right? This is A and this is B. They will just stop before colliding each other, right? Since deceleration is same for both the trains and initial velocity is also same for the both trains, right? And the distance between them is 2000 meter. We can say that if they stop just before colliding, it means that each of the train will be covering a distance of equal to 1 kilometer, right? They must cover a distance equal to 1 kilometer, right? Because they will be stopping just at the middle of this platform, right? Because the initial speed for both the trains is 40 meter per second and the deceleration is also equal and uniform. That means that they must stop at the middle of this platform, right? And each of the train must have covered a distance of equal to 1 kilometer, right? We have to calculate the deceleration, right? So deceleration, we can use this equation for any of the train. That's v square is equal to u square plus 2as, and the displacement of each of the train will be from its initial position will be equal to 1 kilometer. So s will be nothing, it will be 1 kilometer, or we can say this s will be equal to 1000 meters, right? And initial speed was given to be 40 meter per second, but the final speed is equal to 0 when they stop. So v is equal to 0 here. So our a will be nothing, a will be minus u square upon 2s, right? So minus u square means minus 40 square upon 2 into 1000, right? So it will be minus 1600 or 1000, right? Or 2000. So it will be minus 16 over 20, or we can write it as minus 4 upon 5 meter per second square. So this should be the deceleration for both of the trains, so that they just avoid the collision between the two trains at the middle of this platform, right? And we have one more question. It's a very important question, right? It's a very beautiful question. The question is that the position as a function of time is given as, for a particle, the position as a function of time is given as 8t minus t square, right? 8t minus t square. It's a position versus time function, right? Position time function, right? So position is given as a function of time, right? We have to calculate the displacement and distance traveled by this particle between the time interval 0 seconds, t1 equal to 0 seconds, and t2 is given as 5 seconds, right? We have to calculate the displacement as well as distance traveled by this particle, right? So if we calculate the initial position, displacement is nothing. That's delta x vector. So that will be nothing. That will be equal to final position vector minus initial position vector. And we know that final position vector is nothing. It's the position vector at time t equal to 5 seconds. And initial position vector is nothing. It's the position vector at time t equal to 0 seconds, right? You can see that the position vector at time t equal to 0 seconds is 0. It means that at time t equal to 0, the particle was at origin, or the displacement will be equal to, that is x final vector, right? And the initial position is 0. So we can substitute the value of 5 seconds in the given equation. So it will be 8 into 5 minus 5 square, right? So it is 40 minus 25, that's equal to 15. So 15 meter is the displacement during times 0 to 5 seconds, right? This is the displacement, right? And we have to also calculate the distance traveled by the particle. But before calculating the distance traveled by the particle, we have to make sure that the particle actually moves along the straight line and particle does not reverse its direction during this journey, right? If at any point the particle reverses its direction, then in that case that we know that displacement will not be equal to distance. In that case, we have to calculate the distance, and that will be greater than the displacement. So if in this case the displacement, the particle does not reverse its direction, then it means that the particle has not changed the direction of its velocity, or we can say that displacement is equal to distance, right? But we are not sure whether the particle has changed its direction or not. For checking that whether particle has changed its path or direction, we have to calculate the velocity, right? So our x is given as, that's 8t minus t square, right? If we differentiate this dx over dt, that's our velocity v. It will be nothing. It will be 8t. Differentiation of 8t will be 8, and the t square will be 2t, right? Now we can see that velocity is given as velocity is 8 minus 2t, right? Velocity is 8 minus 2t, or we can say that we can also say that the velocity becomes zero. Velocity becomes zero after some time. Let's calculate that time. The time is nothing, that's t equal to 8 upon 2, that's equal to 4 seconds. So it means that after time t equal to 4 seconds, the particle stops its motion and then reverses its direction, right? So when the particle reverses the direction of velocity at the time of when the particle reverses its direction, the velocity has to become zero, right? Then only the particle can reverse its direction and move in the opposite direction, right? So the particle must be moving like this. The particle moves along a straight line like this, right? And after some time, the particle comes at rest. Let's suppose that A to C, between A to C, this is the point where velocity becomes zero for the particle, right? And then finally, after time t equal to 5 seconds, the particle stops at position B, and AB is nothing, it's the displacement, right? AB is the displacement. So AB is nothing, it's the displacement of this particle, right? And if we have to calculate the distance, distance will be nothing, it is greater than displacement here. So distance will be AC plus BC, right? So this is the total distance, right? AC plus BC. We know BC is nothing, BC, AC plus BC, right? Or we can say that, after time t equal to 4 seconds, the particle stops here, right? It means that particle just travels from this point to this point in next 1 second, right? In next 1 second, the particle travels from C to B, right? From C to B. If we calculate the acceleration of this particle, acceleration will be nothing. Acceleration is going to be equal to minus 2 meter per second square, right? Minus 2 meter per second square. So this is going to be the acceleration, right? So minus 2 meter per second square is going to be the acceleration. Or we can say, we can also calculate the velocity after time. After time 5 seconds. After time 5 seconds, the velocity of this particle is 8 minus 5 into 2, right? That is 8 minus 10, or that's equal to minus 2 meter per second. Or we can say that the velocity of this particle at this point is nothing, it's 2 meter per second in the reverse direction, right? And the acceleration is minus 2 meter per second square. So if we apply equation of motion between B and C, equation of motion between B and C, that is between B and C, if we use this equation, that is V square is equal to U square plus 2AS, right? Correct? Our u is 0 because at the point C the particle stops and reverses its direction, so u is equal to 0. And v we calculated, it is equal to minus 2 meter per second square, so it will be minus 2 ka whole square, right? Minus 2 ka whole square, and we'll be left with the value of the deceleration here is that's equal to 2, right? That's 2, and we'll be left with s. So the s is nothing, that's our equal to bc, right? S is equal to bc, that will be equal to 2 square upon 4, right? That will be equal to 1. So it means the distance traveled between C and B is equal to 1 meter actually, right? That's equal to 1 meter, correct? So that's equal to 1 meter. Distance between B and C is equal to 1 meter, correct? And the displacement was equal to, in the previous question, displacement came out to be 15 meters, right? It was 15 meters. Now the total displacement distance is nothing, that's AC plus, that's equal to AC plus BC, right? Our AC is nothing. Our AC is nothing. BC comes out to be 1 meter, right? BC is equal to 1 meter, right? BC is equal to 1 meter. And if from here to here, BC is this is also a BC, right? If this is 1 meter, then this also should be 1 meter, right? And we know from here to here, from A to B, the displacement is equal to 1 meter, 15 meters. So AB is our 15 meters. So it means our AC is nothing. It's 15 plus 1, that's 16 meters, right? So 16 plus 1, that's equal to 17 meters. So the total distance traveled by this particle between A and B is 17 meters, right? And acceleration of this particle comes out to be minus 2 meter per second square. And the velocity after time t equal to 5 seconds is 2 meter per second. So the total distance is 17 meters, and we know that 17 is greater than 15. So here distance is greater than displacement, right? In the last lecture, we discussed about the four equations. We discussed about the v is equal to u plus at, and we also derived v square is equal to u square plus 2s, and then s equal to ut plus half at square, right? But in this, here we'll be deriving one more equation of motion, that is to calculate the distance traveled by the particle in nth second, right? Let's suppose that let's suppose that the particle is moving with some initial velocity u, right? It's moving with some initial velocity u at time t equal to 0, right? And after some time t, or we can say after some time t equal to n, the particle reaches at this point, right? After t equal to n, the particle reaches at this point, and the distance traveled by this particle is equal to Sn. And this particle is moving along the straight line, right? And suppose that the 1 second before this time t equal to 1, the particle would have been here, right? The particle would have been here. So let me call this distance traveled by this particle in the time t equal to n minus 1 second, right? And let me call this distance as from here to here as Sn minus 1, right? So the distance traveled by this particle in the last second or nth second is nothing. So distance traveled by this particle, let's suppose that's equal to d. That's equal to d, correct? That's equal to d. So that will be nothing. That will be equal to Sn minus S of n minus 1, right? So this will be the distance traveled by this particle in the nth second, right? In time t equal to n second, the particle travels a distance of Sn, and in time t equal to n minus 1 second, the particle travels a distance of Sn minus 1. So in nth second, the particle will be traveling a distance of Sn minus 1, right? So this is nothing, this is distance traveled in nth second, right? This is the distance traveled by this particle in nth second. We can write this Sn as u into n, because time here is equal to n, that's u into n plus half an square, right? Correct? And our Sn minus 1 will be nothing. We replace n with n minus 1 plus half a n minus 1 ka whole square, right? So it will be half a n minus 1 ka whole square. So the distance in the nth second is, that's t equal to sn minus 1, that's equal to un plus half an square minus un minus 1 plus half an minus 1 ka whole square, right? So we'll just expand it. So this is un plus half an square minus un minus u plus half a. So it will be n square plus 1 square minus 2n, right? Minus 2n. So it will be un plus half an square. We'll multiply with the negative sign for all the terms here. So it will be minus un plus u, right? Minus an square by 2 and minus a by 2, right? Minus a by 2. Then finally we'll be left with plus an, right? Plus an. So plus half an square will go and minus half an square will also cancel out. Un plus un, this will also cancel out. We'll be left with u minus a by 2 plus an, right? Can take a as common here. That's plus a n minus 1 by 2, right? Or we can rewrite it as u plus a into 2n minus 1 upon 2, right? So this will be the final equation for the distance traveled by this particle in the nth second. So t will be nothing, it will be u plus a upon 2, 2n minus 1, right? So this is the final equation, right? This is the distance traveled by the particle in nth second, right? So u plus a by 2 into 2n minus 1. So this is the final equation. So let's solve one question related to this. The question is that a body starts from rest. What is the ratio of distance traveled by the body during the fourth and third second, right? The body starts with rest, means u is equal to 0, and we know that distance in nth second is nothing. That's equal to u plus a over 2 into 2n minus 1, right? And we have to calculate the distance in fourth second, that's d4. That will be a over 2 into 2 into 4 minus 1, right? And our d3 will be equal to a over 2, 2 into 3 minus 1. Taking the ratio of both, that's d4 over d3. So it will be nothing, it will be 8 minus 1 over 6 minus 1, right? So it is 7 over 5. So 7 over 5 will be the ratio of distance traveled by the body during fourth and third second. During fourth and third second. So this is the final distance traveled by this body during fourth and third second, right? Now let's discuss about motion of a body under gravity, right? Motion of a body under gravity. Let's suppose that this is the ground here. This is the ground here. And what we are doing is that we are projecting a body vertically upward, right? with velocity. Let's suppose the velocity is u, correct? The velocity is u. The body has been projected vertically upwards with the initial velocity u, and we know that the only force acting on this body is the force due to gravity, and the acceleration because of that force is the acceleration due to gravity, that's vertically downwards, right? So A is equal to, that's equal to G. It's nothing, it's minus 9.8 meter per second, right? Per second square. And one of the important thing about the motion under gravity is the sign convention, right? Is the sign convention. So all the directions in the upward, all the vectors in the upward direction will be taken as positive, right? And all the vectors in the downward direction will be taken as negative, right? So all the quantities which are in the upward direction, will be taken as positive, and rest of the quantities which are in the downward direction will be taken as negative, right? In the same manner, if suppose we have to take the sign of this u vector, we'll be taking it as plus u, right? Because it's initially in the upward direction, we'll be taking it as a positive direction, right? Similarly, if we talk about the case second, in case of motion under gravity, case 2, suppose that the same body is being dropped. The same body is being dropped or released from some height h, right? From some height h. From height h, the body is being dropped. If the measurement is done from this ground, right? This is our reference point. This is our reference point. If the ground is our reference point, it means all the measurements will be done from this point O, right? Then this height h will be taken as positive, right? Because it's in the upper direction, right? From this reference point O. And suppose this body is released, then the initial velocity will be equal to 0, right? And the acceleration due to gravity is once again g, that's vertically downwards. And this acceleration will be once again taken as negative, right? That's minus 9.8 meter per second square. Because the direction of this acceleration is once again in the negative direction, right? So we'll be taking it as negative, right? And all those quantity which are in the upward direction will be taken as positive, right? So the acceleration due to gravity will be always taken as negative because it's always directed in along the negative y direction, right? It's always directed along the negative y direction. Let's suppose that, let's talk about the case 3. Let's suppose that we have a tower here. This is the building here or tower here, right? This is the tower here, right? And let's suppose the height of this tower is equal to h. The height of this tower is equal to h. And what we are doing is that there is a person here, right? The person is standing here on this tower. And what this person does is that it releases a ball, right? It releases a ball. If we say the ball is released or dropped, it means that the initial velocity given to the ball is equal to 0, right? And if suppose that we're taking this as origin, we're taking this as our reference point, right? The height of this tower is taken as reference point. If this is our reference point, then all the measurements which are in the downward direction will be taken as negative, and the measurements which are above this reference point will be taken as positive, right? So all these quantity in the upward direction will be taken as positive, and rest of the quantities in the downward direction will be taken as negative, right? And with respect to this reference, the initial position of this ball was equal to 0, and the final position is here. That's x final is equal to, that's equal to minus h, right? Because it's in the downward direction. Now, the final position of this particle will be taken as minus h when this particle strikes this ground, right? So the final position will be taken as negative, or we can say the displacement is nothing. The displacement will be taken as uh, final position vector minus initial position vector. So with respect to the reference point, which is taken as the height of this tower, that's the reference point, or the point where this person is actually standing, is taken as the reference point. Then initial position of this ball with respect to this reference is 0, and the final position is minus h. So it will be minus h minus 0. So the displacement here will be taken as negative, right? So the displacement will not be positive, it will be taken as negative, that's minus h, correct? So that's where the reference point becomes very important, particularly in this case, or any case, right, where the vectors are involved. The sign conventions become very important. All it's your choice, whatever convention you take. But if you take some direction as positive, then opposite to that direction has to be taken as negative, right? But generally, what convention we will follow in this course will be that all the directions which are in the upward directions, right, with respect to the reference, will be taken as positive directions, and rest of the direction which are opposite to the positive direction will be taken as negative directions, right? This will be the general convention that will be using everywhere in this course, right? So let's rewrite all these equations of motion. Let's see how these equations of motion will be taking the shape, right? So we know that v vector is equal to u vector plus a vector into time t. We know that here the a vector is in equal to minus g, right? It's in the vertically downward direction. So we'll be replacing a vector with minus g here. So we can rewrite it as v vector is equal to u vector minus gt, right? Correct? So minus gt. Or we can also rewrite another equation as displacement vector, that's u vector t minus half gt square, right? Or we can write it as v square is equal to u square minus 2gs, right? Correct? Or for the distance in nth second, that will be equal to u plus u minus, that will be equal to u minus u minus g over 2 into 2n minus 1, right? U minus g over 2 into 2n minus 1, correct? And let's discuss a case first, right? Let's suppose that a body is placed on this surface, right? On this surface, and the body is placed on this surface and it is projected vertically upwards, right? It's projected vertically upwards with speed u. Then we have to calculate the time taken by this particle to reach its maximum height, right? So let's suppose that after some height h, this particle stops its motion, right? And when the particle stops its motion, its final velocity will be equal to 0. So the time taken by this particle to reach this height, let's suppose that's equal to t. So this t will be nothing. It will be equal to, we can use the equation of motion, that is v is equal to u minus gt, right? And v is 0 here, or our t is nothing. It's u over g, right? U over g. And let's try to find what is the time taken by this particle uh, to get back to the same position, right? From this maximum height, right? The particle will be moving like this and it will strike back on the surface, right? So the time taken by this particle will be, suppose for this case now, the initial velocity will be equal to 0 and this particle will be uh, striking with some velocity, once again with the same velocity u here, right? So that will be equal to v, correct? So we can use the same equation, right? The final velocity will be equal to v, right? And the initial velocity is nothing. Final velocity will be taken here as minus v. We know that this velocity is now, final velocity is directed along the negative direction, so we'll be taking it as minus v, right? And the acceleration is once again negative, so we'll be taking as minus g, and the initial velocity is 0. So the time once again will be equal to u over g, right? So it means that motion under gravity is a symmetric motion, right? Whatever the time taken by this particle from 0 to maximum height is taken, and same will be the time taken by this particle from maximum height to the ground again, right? So we can say that the total time taken by this particle during this journey will be nothing. It will be 2u over g, right? It will be 2u over g, right? And we can also calculate the height attained by this particle when the velocity becomes 0. So we can use this equation, that v square is equal to u square minus 2g h. Let's suppose that h is the maximum height, right? So h is our maximum height, correct? So we can calculate the value of height also, right? So the final velocity will be equal to 0 when the particle stops. So v will be 0. So we'll be left with minus u square, that's equal to minus 2gh. So our height h is nothing. That's equal to u square over 2g. So this is the height the particle always attains when it is thrown with a velocity of u, vertically upward direction, right? So u square over 2g is the maximum height attained by this particle, right? And one more important point is that the particle can be at same height at two different times, right? Particle can be at same height at two different points. A particle in a motion under gravity, particle in a motion under gravity, particularly when the particle is projected vertically upwards, right? Vertically upwards. A particle in a motion under gravity can be at two different positions. Can be at same positions. Can be at same positions. Can be at same position. Same position at different times, right? At different times. If this particle can be at same position at different times, it means that suppose we throw a particle vertically upwards, right? If we throw a particle vertically upwards, and let's suppose the particle moves with some velocity u, and initially the particle is let's suppose at time t when the particle is at position x1, right, from this ground, and after some time the particle goes up and comes down, right, and after time t equals t2, right, the particle is once again at the same position, right, and the particle comes back, right, the position is once again x1. So we can see that the particle can be at can be at same position at two different times, right? And similarly, in case of projectile motion, you'll be seeing that the particle can have same positions. The particle can have same height, not positions, right? Particle can have same height or two vertical positions, right? At different times, right? The particle can have same vertical positions, right? Particularly, I am mentioning a vertical positions, right? So the particle can be at two same vertical positions, right, at two different times. That will be studied in the projectile motion. But here, in case of vertically upward motion, right, the particle or the body can be at two different times at the same position, right? So in the next class, we'll be discussing about the graphical analysis of this motion along a straight line. We'll be discussing about the position time graph, velocity time graph, speed time graph, and then acceleration time graph, and different various parameters that will be drawn from all those graphs, right, will be studied in the next class, right? So till then, take care and goodbye.